Hi, welcome to the Iowa State Geometric Analysis Seminar. Our speaker today is Xuan Hien Nguyen, who's a professor here at Iowa State. Before coming here, she was a postdoc at Kansas State and University of Cincinnati. She obtained her PhD in 2006 from University of Wisconsin-Madison, working with Sigurd Antonen. Today, she'll be discussing the fundamental gap for horoconvex domains in hyperbolic space.
Thank you for coming and listening to my talk. I advertise it as so this is the first part of a two-part talk. I will go over the background and a easier result, and then in the next talk, I'll get to something that is a little more involved. So let's do the introduction to the fundamental gap. We are mainly looking at eigenvalue of the Laplace operator. We have a bounded smooth domain omega. Here, omega is going to be in Rn for a while, and then I will tell you what happened on the sphere and on hyperbolic space. It is, so the equation is Laplace phi equals minus lambda phi. We are looking at Dirichlet boundary condition, and it is well known that the first eigenvalue is simple. And the second is going to be strictly greater than the first then. There has been many work on Dirichlet boundary condition, Neumann boundary condition, and also Robin mixed condition and Steklov. The basic tool, and as I said, I will stick to Dirichlet boundary condition for this talk, is a min-max principle, also called as the Rayleigh Quotient. It's known as the Rayleigh Quotient too. So I'll skip over here. The first eigenvalue is the infimum of the integral of gradient phi square over the L2 norm of phi. This is a normalizing factor, otherwise you can just multiply the function by constant. And the second eigenvalue, you still take the infimum, but over all of the functions that are perpendicular to the first eigenfunction. So the gap between the first and second eigenvalue of the Laplacian, or more generally, we can add a potential and treat the same problem but with Schrödinger operators, is called the fundamental gap or the mass gap. It's denoted by gamma omega, and it's simply lambda 2 minus lambda 1. Estimating it is very important both in mathematics and physics. As an example, it's lambda 1 kind of tells you the energy of the stable state, and lambda 2 would say, hey, what is the energy of the next excited state? So it's like, how much energy do we need to jump from the stable to an excited state? The problem is, well, can we estimate this gap? Can we have optimal upper and lower bounds for the gap? The first example is very easy. So if we have an interval, a one-dimensional interval from 0D, we solve phi second plus lambda phi equals 0. We write this. So it's the solution. This is an ODE problem. It's going to be phi equals C1 sine square root of lambda x plus a second constant cosine square root of lambda x. Yes, this is the general solution. Now let's look at some boundary condition. I told you it was Dirichlet boundary condition. So phi is 0 at x equals 0. This means that this goes. And the second boundary condition, so C2 is 0. The second boundary condition is phi is 0 at x equals d. That means that sine of square root of lambda d is 0. So square root of lambda d is k pi. For, well, both numbers are positive, so k equals 1, 2, etc. We don't want 0, otherwise we get phi equals 0, which is the trivial function. Now, what is the first eigenvalue? K equals 1 gives you lambda 1 d square is pi square. So lambda 1 is pi square over d square. And k equals 2, you can do it in your head now, and it's 4 pi square over d square. So here the fundamental gap is lambda 2 minus lambda 1, which is 3 pi square over d square. So that's the first example. The second example is only slightly more complicated. It is now a rectangle of length L, and the height is epsilon. And yes, epsilon is going to be much smaller than L. We have done this too in graduate courses. So separate variable, phi, I write it as h of x times f of y. And so the equation becomes f y y h plus h x x f plus lambda f h equals 0. And let me put this together. Now we divide by fh, and I get fyy over f. And I put the rest of it together. So hxx over h plus lambda equals 0. This is going to be a constant because it's a function of y plus a function of x only. So this is a constant. And this is only also a constant. And we've seen in the previous example that the constant, if you write fyy equals constant times f, the good constant to take is going to be minus k square pi square over epsilon square, which is our lambda in the one-dimensional problem. And here k equals, let me write it below, k equals 1, 2, etc. Now I stick this constant into the other side, so I have hxx over h plus lambda is k square pi square over epsilon square, same constant. So hxx plus lambda minus k square pi square over epsilon square h is 0. So lambda equals, well, let me write one line here and then minus k square pi square over epsilon square. Now this is the same setting as the 1D problem, and we saw that it was a integer, I call it L square, pi square over the length square, which is L square. So now k is 1, 2, anything. L is also 1, 2, 3, So what is the smallest eigenvalue? Let's show this and see if I can make it smallest because I need more room. Oops. Okay, so the smallest eigenvalue, lambda 1, is 1, k is 1, and L is 1. So it's going to be L square pi square, oh, L is 1. Pi square over L square plus pi square over epsilon square. Now for the second eigenvalue, I have a choice. I can either take k equals 1, L equals 2, or k equals 2, L equals 1. That would be the candidate for the next smaller one. Now, epsilon is very small, so it's better to take k equals, to put it in front of the pi square over L square. So the second eigenvalue is going to be 4 pi square over L square plus pi square over epsilon square. So which one is that? That was L equals 2, so not this one. Again, the fundamental gap is lambda 2 minus lambda 1, which is 3 pi square over L square. Now, as epsilon goes to 0, L will tend to the diameter, which is the diagonal of the rectangle. So lambda 2 minus lambda 1 will converge to 3 pi square over d square. And this quantity will play a role in the fundamental gap conjecture. So here are some results and conjecture about convex domain in Rn and Sn. So we're going to look at bounded convex domain in Rn. I will talk a little bit about why we need convexity to make the problem interesting. A lot of the results are about Schrödinger operator, which is slightly more general than just Laplace. So it's Laplace plus the potential V, where V is non-negative and convex, with Dirichlet boundary condition. So the fundamental gap conjecture says the fundamental gap, remember it's lambda 2 minus lambda 1, is greater or equal than 3 pi square over d square, where d is the diameter. The lower bound, as we've seen in the previous example, is approached when v equals 0 and the domain is a thin rectangular box. So it's actually a sharp constant. And I said the convexity makes the problem interesting. I will talk about that a little later. So it was a conjecture that has been standing for a while. Here was the progress in Rn. They first prove it's pi square over 4d square and pi square over d square for potential. Then they did it in one dimension. Yes, we did it in one dimension, but there's a potential here that makes it more interesting. And Ben Andrew and Judy Clutterbuck in 2011 solved the conjecture. So they did prove that the fundamental gap is greater or equal than 3 pi square over d square. For triangle, it's a little bit higher, 64 pi square over 9d square. For a convex domain in Sn, it took, so now it's not Rn, but Sn. It took, so you see there's a big gap between 93 and 2019. And the reason is that all the things after 2011 use the same method as the Andrews-Clutterbuck proof of the fundamental gap conjecture. So using the results and the ideas of the proof in Rn, Seto, Wang, and Wei were able to do it with diameter less than pi/2. That means if it stays in a hemisphere. And then we have two papers that says, well, you have the same lower bound for the fundamental gap in Sn. It's not clear what the limiting case is. So it's unclear that rectangles would be the limiting case because it's quite difficult to compute and separate variables on the sphere. So I was at a workshop with Xuan Wei and Judy Clutterbuck, and the question is the fundamental gap conjecture true in Hn, which is hyperbolic space? So it's true in Rn, it's true in Sn, is it true in hyperbolic space? But first, I'm going to explain why convexity makes the problem interesting. So if you don't have a convex set, there's really nothing. First, in R2, say you have a ball, well, a disk, and you look at lambda 1 here. You can separate variable. This is going to be the graph of, I call it phi 1. And it's going to be positive. We can multiply it. It has one sign. But if you have another ball, so, sorry, a disk, then you still have a lambda 1 here. These domain disconnected. And you can also have this guy. Okay, so this would be your first eigenfunction in the first one and in the second one, in your second disk. The second eigenfunction, well, I can say, hey, it can be this guy, and here it's this. I know it's not super. What do I mean by second eigenfunction? It's the same. It's disconnected, so I can flip one side or not. But bear with me for a second. Now, what happened if it's a connected domain? So disconnected, this showed that disconnected, it's really not that interesting because the second eigenvalue is exactly the same as the first eigenvalue. You just flip the eigenfunction on one of them. If it's connected but not convex, but there's a very thin neck between the two. Oh, by the way, the second one looks more like a disk. Then the first eigenfunction is still going to look, so this is a perspective view of my domain. The second eigenfunction is going to still look like this. It's going to be very close to, these two are very close. Here in the neck, it goes down to 0, and it does that. Okay. That's going to be the first eigenfunction. The second eigenfunction, it does a little bit like the second eigenfunction here. It's going to look like this. This goes close to 0, and at some point you'll be able to flip it, and that would be the second eigenfunction. The second eigenvalue will be close to the first eigenvalue as the size of the neck goes to 0. So this was shown there are results that says if you have two convex domain that are connected by a very thin neck, then the behavior of these eigenvalues will be like this. So if you don't impose convexity, you can always do this, and so the fundamental gap will go to 0. I will do a review of hyperbolic space, a very short review, and then I will talk about convexity. So hyperbolic space, there is a half-plane model, which looks like this is the metric, is dx squared plus dy squared over y squared. And the geodesic, so it's only this half plane, which now I proceed to erase to make room. Geodesics are vertical lines, or half circles that meet perpendicularly with the horizon line. You can also have the disk model, which you can send one to the other by an inversion. ds squared is 4dx squared plus dy squared over 1 minus x squared plus y squared, everything squared. But this is sort of infinity. And the geodesics are circles that meet the boundary perpendicularly. So what do I mean by convexity? Let's go through this. So convexity in R2 means that if you have a domain, so in R2, let's write it here. If you have a domain and you take any 2 points, the line segment between the point is inside the domain. But what is a line segment? A line segment can be seen two ways. It's the shortest path between the 2 points, or it's the limit of larger circles to the point. So I can take, let's do this circle. I can take a circle that's larger. I can take a circle that's even larger. And as the radius goes to infinity, these segments will go to the line, which is the same thing in R2. It's kind of silly to think of it both ways. But in hyperbolic space, if you look at shortest path between 2 points, it's the equivalent of geodesic. But if you look at larger and larger circles, you get what's called a horocycle. So that's a typo. There's a little C missing here. Let me show you in the Poincaré model. So suppose you have 2 points. The geodesic would be this guy. Okay. And the horocycle, so I will draw it, erase it, draw. This is a circle. Then I take a larger circle. And then I take the circle of radius, quote unquote, infinity. And it's the circle that's going to be tangent to this. The crazy, well, interesting thing is you could have taken a circle this way and made it larger and larger. And that would give you the second horocycle through these 2 points. So the notion of convexity is given any 2 point, the geodesic connecting those 2 points has to be in the domain. Horoconvexity means given any 2 point, any horocycle connecting those 2 points has to be in the domain omega. Horoconvexity implies convexity. Horoconvexity is stronger than convexity. Well, a straight example is the line segment here. It's convex, but it's not horoconvex. For it to be horoconvex, it has to include the lens. So this is the smallest horoconvex domain that would include these 2 points. And this is the smallest convex domain that includes those 2 points. Convexity, if you want to see it, so I just showed it to you. I forgot I had this thing here. So if I get 2 points, that would be a convex domain. And the horoconvex domain would have to be like this. In the half plane model, for example, this thing get it here. This part of the rainbow that I'm coloring in purple is convex, but not horoconvex. Okay. So what are horocycles in here? Horocycles are circles touching here or horizontal lines. This is a horocycle too. So for example, if I'm trying to connect these 2 points, this horocycle is not in the domain. So that's convex, but not horoconvex. Purple is convex, but not horoconvex. So all your work in Hn, there are convex domain in H2, such that the first eigenfunction is not log concave. Log concave means the log of phi1 is concave, and not even quasi-concave. So log concavity was a property that was used in earlier results about the fundamental gap, not the final one, but it was useful to prove that it was greater or equal than pi over d squared. And the second result that's known in Hn, so there are not too many results, is that for bounded domain, we don't need convexity condition if a ball has the same first eigenvalue, then the ball maximizes the second eigenvalue. Okay. So the first eigenvalue is the same. The fundamental gap of the ball being bigger than the fundamental gap of the domain means the second eigenvalue of the ball is bigger than the second eigenvalue of the domain. They did that to some rearrangement of space and points of the domain. So this is a plug for next time. So we looked at convex domain, and we proved that there is a convex domain, so that violates the fundamental gap conjecture. So for which the fundamental gap is less than 3 pi squared over d squared. It was the same example that didn't have a log concave first eigenfunction. And I plan on proving this thing next time. In fact, it's true for any epsilon. So if you give me any epsilon, I can find a domain for which the fundamental gap is less than epsilon pi squared over d squared. And this is convex. So the next question is, well, what happened to horoconvex, which is more restrictive, and maybe there is a lower bound on the fundamental gap. So for horoconvex domain, is there a C for which the fundamental gap is greater or equal than C over D squared, where D is the diameter of the domain. Oh, and another plug for next time. The thing about this one, so the first result we had, the domains were very large. And it made sense because there's a lot of space in H2, and maybe if you do very large data in H2, they really differ, like they're very different from what happens in R2. And here it says for any diameter. So even I can even find small domains. And the intuition in differential geometry is that if you are in a really small ball, then everything kind of looks like Rn. So everything should behave like Rn. But in fact, this result showed that even for a very small diameter, I can find a domain for which the fundamental gap is less than epsilon pi square over d square. So what about horoconvex domain? The answer is also no. In fact, for horoconvex domain, we can find a constant for which the fundamental gap is less than the constant over d cubed. That means that lambda 2 minus lambda 1 times d squared goes to 0 as d goes to infinity. So the idea of the proof is to show that the theorem is true for geodesic balls. So yes, it is true for balls. So balls are the most convex thing you can ever hope. If you define convexity and balls don't satisfy your definition of convexity, then there's probably something wrong. Balls are really nice and convex, any type of convexity. And then we compare horoconvex domains to balls and prove it for general horoconvex domains. So how does the proof goes? Let me go over this a little quickly. So first, we have this ODE. And in HN, as in SN or RN, if you're doing balls, you can separate variables. And you think of it as the radial function will satisfy this ODE. And somewhere in the literature, there is this amazing change of variable, really nice, that convert this problem into something that looks like a linear ODE, except for this term. And you see sine square of t would go to infinity, so this term goes to 0 when t is large. So it behaves almost like a linear ODE. When n equals 3, and that's the case I will talk about, and then I'll tell you how to do other cases. When n equals 3, this goes away for the first eigenvalue, and you just get a linear. So remember, n equals 3 means this is 2, this is 2, so it cancels with the 4. So it's just the extra u here that gives you the 1. And so lambda 1 is 1 plus pi squared over r squared, like in our 1D problem. The second eigenvalue is, again, after separating variable, making a change of variable, we get this equation. Now, yes, the only difference is a different coefficient here. So solving the problem on or finding what the values are on the ball is simply solving these ODE or estimating it. So when n equals 3, remember I computed lambda 1, and this is the ODE for lambda 2. The idea is to take this eigenfunction, which is the eigenfunction for lambda 1, and set it into lambda 2, set it into the Rayleigh quotient I talked about at the beginning, and see what comes out of it. So the Rayleigh quotient, remember, you just multiply by u and then divide by integral and do a integration by parts here. So it's just the integral of gradient u squared plus when n equals 3, this is just 1, so plus u squared. And here is just 1 half times 4, so that's 2. And it's just u square sinh square t lambda 2, and you divide by the norm of u square. So when you divide by the norm of u square, so lambda 2 is the infimum of that. You get, this guy gives you 1. This guy got this one because I put in v, and this one gives me this one when I put in v. So the integral of gradient v square is pi square over r square. That's a simple integration. And here I have 2v square over sinh t square. So remember, v is a sine. So if I use sine x is less or equal than x, then what is v square? V square, if I approximate it, it's by what's inside. So v square is less or equal than 2 over r. Let me erase some of this stuff. And pi square t square over r square. So this is what I wrote over here. And I have t square over sinh t square. So I spent a little bit of time estimating it in the first version of the article. And then it happened to be that you put it on Wolfram alpha and it spits out, hey, that integral is pi squared over 6. It's probably a contour integral with some complex analysis. I don't quite know how to prove it, but that integral is pi squared over 6. The upshot is that now I have an estimate of lambda 2, which is less or equal than 1 plus pi squared over r squared times a cube. And when you subtract lambda 1, all of this go away. And so the fundamental gap for a ball is of order r cube. In general dimension, we don't have this lambda 1 equals 1 plus pi squared over r squared, but somebody else has proved this. And if you see, it's very nice because this will erase this term, and what is left is stuff in r cube. So for ball is a cubic, 1 over r cube. Then I approximate horoconvex domain by balls. And what I mean is this. If you have large, so in H2 and also in Hn, it's a homogeneous space. And in H2, let's use some complex analysis. If you have any 2 points, you can do a Möbius transformation or Schwarz transformation. And then say, here's how you do it. You take the geodesic that connects the 2 point, take the midpoint, And you can send the midpoint here to the origin while keeping the circle at the boundary, the circle at the boundary. So this becomes here, and these would be up and down. So any 2 points can be sent to these. Now, what are the horocycle? Horocycle is this guy, and it's this guy. If the diameter is larger, so think of these as the 2 points achieving the diameter, then these 2 points would be here. And the horoconvex domain will be like this. And the horoconvex domain has to at least contain this lens over here. So as the diameter gets larger and larger, the lens kind of gets fatter. And it's also not that hard to compute. For example, if you have this to be the diameter, then, and this to be little r, okay, this is the inscribed ball. Inscribed ball. You can compare little r to the diameter. And it's actually the next result. As the diameter gets large, a horoconvex domain becomes rounder. If omega is a horoconvex domain, then it's in radius, which is the radius of the inscribed disk, and the circumradius, which is the radius of the circumscribed disk, satisfy this inequality. So, of course, the diameter is less than 2 times the radius of the circumscribed disk. Now you put r on this side multiplied by 2, you get 2r plus 2ln2. So a horoconvex domain of diameter d contains a ball of radius about d over 2. And when d is greater than some constant, this quantity is certainly bigger than d over 4. So if you have a horoconvex domain of diameter d, it will contain a ball of radius at least d over 4. So at least that's what we do to compare. Then we use the result I quoted. Ben-Gurion and Linde say that in hyperbolic space of 2 convex domain with the same first eigenvalue, the ball has the biggest second eigenvalue. So now I can take a ball of radius r omega that's going to be bigger than the inscribed ball that has a radius greater than d over 4. I know that will be my ball with the same first eigenvalue, but then the fundamental gap of that ball would be greater than the fundamental gap of omega. And we show that this is about 1 over r squared, r to the 4th. 1 over r, cube. So that's true for horoconvex domain too. So what are we working on now? Well, we don't really have an idea of how to do this. It seems like there has to be a rate. What rate is it? It has to be a function of the dimension, a function of the diameter. We showed that 1 over d squared is not the right one. Maybe it's 1 over d cubed. But what is the rate as d goes to infinity, at which the fundamental gap goes to 0? And it's the first eigenvalue log. So this is eigenfunction log concave in a horoconvex domain in Hn. So working on this, it looks pretty hard because horoconvex domain, not sure how to characterize it or write down equation. This seems to be doable because, as you saw, all of the, it's only ODEs, and it's not even looked that hard of ODEs. And we know how the eigenfunction look like. They kind of look like the one without the 1 over sinh square term. But estimating seems quite hard. So that's the work we're doing now. And thank you. If you have any question, I'd be happy to answer them.